Okay, so exam 2 is going to cover basically everything since the last exam. You may notice on this practice exam, though, that we've got some problems that are more related to chapter 4. And that's just because the way this instructor made the exam, they covered a little bit of chapter 4 on one exam and the rest on the next exam. So it's good review either way. But let's go through. But if you have questions, you're always welcome to chime in, let me know, and we can slow down and try to explain things in a little bit more detail. Okay, so the first one's looking at heptane, and it's saying if you burn heptane, you're going to produce carbon dioxide and water. And it's asking for the best coefficient in front of the carbon dioxide in the equation after bouncing. Okay, so what they're really looking for here is what goes right here. But in order to solve that, we need to bounce the entire equation. We can't just guess without bouncing the equation. So looking at this, I'm noticing a few problems right away. The first thing that I'm immediately noticing is if I start with carbon, I've got 7 carbons over here, but I've only got 1 on this side. So what I could do is I could throw a 7 in front of there to try to bounce out the carbons, right? But then if I do that, and go to the next one, I'd say, well, I've got 14 hydrogens here, and I only have 2 there. So maybe I'll throw a 7 in front of my water in order to make that bounce. Okay, so now I've got carbons and hydrogens bounced. But now the tricky part, I've got 2 oxygens here, but over here I've got 14 plus 7. So I've got 14 plus 7, I've got 21 total oxygens. So there's no number I can multiply this by in order to get to 21, right? Because 21 is an odd number. So the question is, well, what do you do when you run into these situations? Well, my general rule of thumb is if you get stuck, try to double your most complicated molecule. So when I look at this, I'd say, all right, let's just try this again. But this time I'm going to throw a 2. Let me make this pen smaller. In front of my most complicated molecule, which is going to be my heptane. And I know by doing that, I'm going to need 14 over here, and I'm going to need 14 over here. So I doubled those. Okay, so now let's go and reassess this. So now I've got 2 oxygens over here. And over here, I've got 14 times 2, which is 28 oxygens from the CO2s. And I've got 14 over here. So let's see, 28 plus 14 would be 42, right? So now it's an even number. So if we think, well, what number could go in front of here? Well, it must be 21. So we could say, well, now it would be bounced with the 21 there. Okay, but going back to the original question, they weren't looking for a completely bounced reaction. That's just good practice. They were looking for the coefficient that went in front of CO2. So this would be 14 for that problem. Makes sense? This one was a pretty tricky bouncing one, but it's good if you get stuck not to get in that panic mode. And like I said, my trick is just double your most complicated molecule, and sometimes you can figure it out that way. Okay, and then number 2, what is the oxidation number of platinum and potassium hexachloroplatinate? So this one's a little bit weird to think about. But platinum, if we think about it, is in that middle section of the periodic table. It's that transition element block, which means it's really hard to predict its charge and hard to predict its oxidation number. But let's try to figure out what's going on here. Let's start with potassium. Potassium's in group 1A, which means it should be an oxidation number of +1. So I'd say +1 times 2 atoms means that both potassium atoms, if we can combine them together, is going to be the same thing as an overall net oxidation number of +2. Now let's do chlorine right here. Chlorine's in group 7A, which means it would be -1. And we've got 6 atoms, which means that if we add up all the oxidation numbers, it should be -6. Okay, so now the question is, well, what would the oxidation number be for this one platinum atom? And if you remember, the sum of all of the oxidation numbers should equal the charge of the molecule, or in the case of a neutral molecule, it should add up to be 0. So let's think about this. We just said we've got +2, -6, and now we're trying to solve for this. So what I could do is I could say, well, the +2 plus the -6 plus x is going to add up to equal 0. Sorry, this is getting a little messy. Let me even move this over. So now we can solve for x, and we can say, well, x in this case must be the same thing as -2 plus 6. So in this case, if we add this all together, this would be the same thing as a +4, right? So in this case, this is telling us, whoops, sorry about that, that the oxidation number of platinum, in order for everything to add up to be 0, must be +4. So let's go ahead and just write that down. Does that make sense? It's similar to predicting the ionic charge. So if you can go back and practice predicting the ionic charge of some of these ionic compounds, or sorry, the ionic charge of some of the transition metal compounds, you should be able to find the oxidation number. It's going to be the same. You have to infer it. And then let's go to number 3. In the following reaction in the hot water solution, what substance is oxidized? So there's a few things we need to consider here. So let's start out with lead in the first one. And this one is a bit tricky. So we need to find the oxidation number of lead here. Well, in order to do that, we can't do it right off the bat. We actually have to infer it because it's a transition metal. But let's try looking at NO3. Does anybody remember the charge of the NO3 polyatomic ion? It's nitrate.
Is it -1?
It's -1. So it's -1. And then we've got 2 of them, right? So times 2 ions, which means that the sum of them is going to be -2, right? Which means that the lead must have an oxidation number of +2, kind of like we did in the previous example. Okay, so now let's go ahead and look at lead on the other side. Well, same idea. We could say, well, oxygen's in group 2A, or sorry, 6A, so it must be -2, which tells us that the lead must be +2. So in this case, it's kind of telling us that lead is going from +2 to +2. Doesn't look like lead is being oxidized or reduced. So I'm just going to go ahead and cross out B there. Okay, so now let's try the next one. And in order to do this, I'm going to kind of look at NO3 over here. So we've got NO3, and we said that NO3 has a charge of 1-. So we're just going to focus in on that polyatomic ion. Okay, so oxygen, if we think about oxygen, oxygen always has a charge of -2, right? And in this case, we've got 3 atoms, right? So it's going to equal to a sum of -6. All right, so now the question is, well, what's the charge going to be for our nitrogen? What do you think? This one's a little tricky.
+4?
Close. So in this case, let's think about it this way. I'm just going to call this x as my variable. So what I'd say is x plus the sum that we just found, -6, is going to be equal to the charge, which we said is -1.
Mm-hmm.
So knowing that, what would it be?
+5.
+5, exactly. So this is a weird one. A lot of times students will say, why isn't it, -3? Well, in this case, because it's closer to the center of the periodic table, it can vary from those ideal numbers. And it would be +5. Okay, but either way, we've got that figured out. So I'm just going to go ahead and erase this and say we've got nitrogen, it's +5, and we've got oxygen, which is -2. Okay, so now let's go over to the other side. Let me even slide this over a smidge so we have more room. Oh. Okay, and on the other side, let's focus in on the oxygens, right? So on this side, we've got two different types of oxygens. This one is a part of a compound, so it's -2. So we could say, well, -2 to -2, that means there's no redox reaction there. Okay, but let's try the next one. What would the oxidation number be for oxygen and O2? Be 0, right? Because it's by itself now. Okay, so in this case, we're going from -2 to 0, which means that it lost 2 electrons, which means that it was oxidized. So in this case, it seems pretty clear that oxygen must have been oxidized, and that leads me to believe that A must be the right answer there. Does that make sense?
Yeah.
This part right here is what always throws students, where they get really hung up on the nitrogen and they say, well, why isn't the nitrogen -3? I would expect it to be -3 if it's ionic. I just made another video that I put in one of the discussion boards, but the further you get away from the edges of the periodic table, the less reliable those charges are going to be, which is exactly why the transition metals are so unreliable. They're in the middle of the periodic table. But even if you're in group, in group 3A and 4A, those often aren't super reliable. You might have to infer kind of like we did here. Okay, next one, question 4. How would you classify this reaction? So this one, we've got a bunch of things going on here, but I'll show you a hint. Anytime you see an element by itself on one side, like chlorine here, where it was a part of a compound on the other side, what do you think that tells you?
I don't know.
It must be a redox, right? Because this is always going to be 0 when it's by itself. But anytime it's a part of a compound, like over here, we would assume that it's ionic, right? So the charge for chlorine over here would be -1. So it means that it must be a redox reaction. So anytime you see something like chlorine by itself on one side, but not on the other side, that means it's likely going to be a redox reaction. That's one really quick way to go about solving these. A decomposition reaction, let's just kind of practice this. What's a decomposition reaction tell you? What does that look like? Let's think about if I were buried in the ground and I decompose. I would be one thing going into the ground, but I would decompose into a bunch of like gas and water and things like that, right? So decomposition starts with one thing, but ends up with many things. In this case, we're starting out with many things and ending up with many things. So I don't think it's a decomposition. A double replacement, I talked about in the video, and the way I like to describe a double replacement is if you go square dancing, or have seen square dancing, and you have two people dancing and you switch partners, that's a double replacement reaction. So that's a good way of remembering those. In this case, we're not switching partners, though. It looks like a bit more complicated than that. So in this case, a redox reaction would be the correct one. The metethetical, I think that's just a made-up word. All right. Number 5, which of the ions in the following reaction would be classified as spectator ions? So a spectator ion is something where it is present on both the left-hand side and the right-hand side. So I could go through and check, and some students would immediately say, oh, well, there's copper on both sides. So that would be a spectator ion. Why isn't that right?
Because it changes charge.
Yeah, it changes charge. In fact, this copper isn't even an ion, so it can't be a spectator ion. a spectator ion has to have the same charge, like you were saying. So next I would go to my hydrogen. Well, over here, it's got a positive charge. Over here, it doesn't have a charge, so it can't be that. And then next, I would look at my bromines and I'd say, it's bromine minus and bromine minus. That means it must be a spectator ion. It's not changing in the reaction. It's just kind of hanging out.
Professor, can I ask a
Yeah, of course.
when you're looking at these redox reactions and you're taking charges and doing things like for oxidation number, you don't pay any attention to the like the 2 in front of the bromine?
Yeah, that's a great question. So when doing redox reactions, coefficients really don't matter.
Okay.
I would just ignore them. They're almost distracting, but it is important to make sure that reactions are balanced for stoichiometry.
Great.
Yep, good question. All right, next page. So the redox reaction shown may also be best classified as what? So there's a few things I'm noticing in this reaction. The first thing that immediately jumps out to me is that heat is a product. So if heat's a product, what does that tell us about the reaction? Is it exothermic or endothermic? Exothermic. So I would go through and I would cross out this one and this one because those are both endothermic. All right, so now the question is it a replacement or is it a synthesis? So in this case, I would say that it jumps out to me that this iodine that's with sodium is swapped out for a chlorine, right? So to me, this looks like a pretty clear example of a replacement. A synthesis is kind of the reverse of a decomposition, where you take many things and turn them into one. In this case, we're not turning two things into one thing. It's still two things in, two things out. They're just swapping an atom. So it would be best described as a replacement. All right, let's do the next one. This one's a little bit harder. So how many grams of CO2 form if 48 grams of CO are combined with excess oxygen? And it says to remember, always bounce your equation. So let's first bounce it. It looks like the carbons are bounced right now, right? We've got one on each side. But now I've got 3 oxygens on the left and only 2 on the right. What should we do if we run into weird situations like that where it's an even odd thing?
Double the biggest molecule.
Yeah, I would just double the most complicated molecule. So in this case, I'll just write 2 in front of the CO here. Okay, so now I've got 2 carbons on the left. I need to put a 2 on the right to get the carbons bounced again. And now when I look over here, between this and this, I've got 4 oxygens. And what do you know? I've got 4 oxygens over there. So it looks like it's bounced now. So I always do that before doing any of the math. And now we can jump into the math. And it says that we've got 48.0 grams of CO are combined with excess oxygen. And it's asking how many grams of CO2 would form. So what should I convert to first? What's the best thing we can always convert to?
Grams to moles?
Yep. I always tell my students, at least in intro-level courses, that moles are the universal currency in chemistry. So if you're ever stuck, try to get to moles. So I'm going to put grams of CO on the bottom and moles of CO on top. And if we look at the periodic table, we can look up carbon, and carbon is 12.01, and oxygen is 16.00. So it's going to be 28.01 grams for every 1 mole. Okay. Now we're not trying to solve for moles of CO, we're trying to solve for CO2. So I'd want to cancel out moles of CO by putting that on bottom. And we can convert this to moles of CO2 by looking at the reaction coefficients. So over here, I'd say, well, we've got 2 moles of CO for every 2 moles of CO2. So it is a 2-to-2 ratio, but I still like to show this just in case it weren't 2-to-2 or 1-to-1. But we're not quite done. Now we need to figure out grams. So I want to cancel out moles of CO2 and get to grams of CO2. And again, I would go to my calculator and try to figure out how many grams of CO2 there are in 1 mole. And carbon is 12.01 and oxygen's 16.00, which means that this would be 44.02. And I like to always double check that my units cancel. So I'm canceling out grams, I'm canceling out moles, and I'm canceling out moles, and I'm getting my desired unit of grams of CO2. So I'm going to just do this in my calculator. Got 48.0 times 1 divided by 28.01 times 44.02. All right, and I should only have 3 sig figs in my answer. So I'm getting 75.4 grams of CO2. And what do you know? That looks like the correct answer would be A here. I'll stick with a red pen. So one thing I have found, especially with Chem 121, is students sometimes feel really stressed with time. The more you practice these, the quicker you are with them, but try not to let one of these math problems take up like half of your exam. You don't want it to eat up too much of your time. So try to, if you can, skip problems that you think might take you more time and then go back to them at the end, just in case. All right, so now the next one, if 20 grams of CO and 20 grams of O2 are combined, what is the limiting reagent? So let's go ahead and bounce this just like we did up above. Luckily, it's the same equation. And let's just do some basic math here, right? So let's say we've got 20 grams of CO. Let me scroll up a little bit so I can see my work. We said that there's 1 mole of CO for every 28.01 grams of CO. And let's figure out how much CO2 we would get. So we'll do the same thing as up above. I'm just going to cancel or omit my units just to keep things simple right now. And let's figure out how much CO2 we would get from this. So I've got 20 times 2 times 44.02. And if I had 20 grams, it looks like I'm going to get 2.87 grams of CO2. Let's try the other one though. So this one is saying, what if we had 20 grams of O2? Well, in this case, there's 1 mole of O2 that weighs 32.00 grams of O2. And in this case, there's 1 mole of O2 for every 2 moles of CO2. So now the bouncing comes into play, right? Because we see that there's 1 mole to 2 moles here. And we know that for every 1 mole of CO2, there's 44.02 grams of CO2. So basically, I'm just trying to figure out which one gives me the most CO2. So I'll do my math here. And I'm getting 55.025, but I should have just left it at 55. Really, we shouldn't even have that many. I would call it 60, but it seems quite clear that this one produces the least. Which means that this starting amount of CO is going to really limit the amount of product we can make, right? So in this case, I would immediately circle CO as my limiting reactant. It's the thing limiting the amount of CO2 we can make. We're going to max out at 2.87 grams. We don't have enough to produce any more than that.
Hey, Jeff.
Yeah.
So for the first one, for the CO, all of my math is the same as yours, but I got 31.423.
Let me double
Okay,
check.
that's
So
the
for the
same.
first one,
Yeah.
I've been known to make calculator errors on occasion. I'm still getting 2.87. Is anybody else getting different answer?
I'm also getting the 31
What am
and
I
some
getting?
change up.
Hey, Becky.
Give me a sec.
Oh, holy cow. I wonder if I have a sticky button on my calculator. I did it twice. You were right.
Okay. I just wanted to make sure.
Luckily, it doesn't change
Change the answer.
the
Yeah.
outcome. So it's 31 grams of CO, and it's still the least, so it still would be the limiting reagent. Sorry about that. My 4 button, I guess, is sticky. I need to get a new calculator. All right, let's do number 9. Tests are to be conducted on new anti-cancer drugs, and you are to prepare a fresh supply for human subject studies. You discovered that you were able to produce 0.983 grams of this substance, although it is possible to make 1.433 grams. What is the percent yield? So it is important to remember that percent yield is going to be your actual mass over your theoretical times 100. So in this case, we were actually able to produce 0.983 grams. Theoretically, it was possible to make 1.433 grams. And we multiply this by 100. And let's do that really quick. I'm getting 68.6.
The same.
What was that? Is that what other people are getting? Okay.
Yes.
I noticed on the key for some reason that it's listing it as 69.6, so that must be a typo on the key, and I'll try to go back in and fix that on the key. I don't know why that happened. All right, number 10 is related to Lewis dot structures. Does anybody want to do this just as a refresher, or should we skip it?
Skip it.
Skip it? Okay, seems like we kind of mastered that on our last exam, or hopefully we did. 11, 1.391 moles of sample gas is held at 4.367 atmospheres of pressure, and the container volume is 40 liters. What is the temperature of the gas? And a few people have asked if I'll give the gas equations. I will, but that doesn't mean you shouldn't know how to use them or which one to select. For this one, I know that I'm being given pressure, I'm being given volume, I'm given the moles. So I would go ahead and do PV equals nRT. This is the ideal gas law. And it's asking what is the temperature. So let's rearrange this to solve for temperature. And I would say that, well, temperature in this case is going to be PV over nR. Okay, so pressure in this case, they give you as 4.367 atmospheres. Volume, they give you at 40.00 liters. The moles, which is N in this case, is 1.391 moles. And then R is going to be our gas constant. And I will give you the constant, but it's pretty useful to remember. It's 0.0821 liter ATM over mole Kelvin. So let's go ahead and plug this all in. I'll make sure my 4 button works.
The other constant for
do you only use that? Do you ever use it for the ideal gas law, or do you for TOR, the one that?
Oh yeah,
is,
that's
like,
a really
the
good question. So the main thing I do is I make sure that all my units cancel. So with this gas constant, you see how I've got ATMs here and here? That means
Yeah.
those are going to cancel. I've got liters here and here, so those are both going to cancel. And I've got moles here and here, so those are both going to cancel. You might find different R values that use different units of pressure, like TOR, but those will have a different number that goes in front of them.
Okay.
Yep, so you can just select the one where the units cancel appropriately.
Okay, cool. Thank you.
And then it looks like for this one, we should have 3 sig figs as our answer. So I'm getting an answer of 1530 Kelvin. That would have 3 sig figs in the answer. Make sense? Okay, and then the next one, calculate the volume in liters of 0.113 moles of gas at standard temperature and pressure. That's what STP stands for. It's not Stone Temple Pilots, which I guess is kind of a dated band. But the main thing to remember is at 1 STP, there's 22.4 liters of gas, regardless of what the gas is. So if we have 0.113 moles, we could say, well, we know that for every 1 mole, there's 22.4 liters. We should be able to solve this really quickly. And our answer should only have 3 sig figs, so this should be 2.53 liters for our final answer there.
So the one above that, number 11,
Yeah.
I am getting a different calculation than that.
Let me double check. Is anybody else getting a different answer?
To tell you the truth, this is going really, really fast.
Oh, no, that's fine. In fact, if I'm going too fast, tell me to slow down. I get carried away sometimes.
Okay.
Let me double check. So the full answer I'm getting is 1529.58, and then it goes on from there. But I wanted to keep 3 sig figs, which is why I rounded to 1,530.
Okay, so I might be doing calculations wrong here. So I'm doing the top, and we've got to multiply those together, and then we divide it by the bottom, which are multiplied together, and I keep getting the same number.
What you may want to do is put both of these in parentheses when you divide.
Okay. Okay.
Because it may be throwing off your order of operations in your calculator.
Okay. Yeah, I'll take a look at that.
Okay, sounds good. Yeah, and like I said, if I'm moving too fast, don't be embarrassed. You can tell me to slow down. In fact, in my organic chemistry class, my students get all fed up with me because I just get really excited about organic chemistry and apparently go way too fast. So, so let's do the next one. It says we've got a 1.432 liter sample of gas, and it's being kept at 27 degrees Celsius at a 88.89 atmospheres. And it says the temperature is raised to 94 degrees Celsius, and the volume is reduced to 0.932 liters. What is the new pressure? So this is a before and after comparison. And there's a few equations that we have where we can do these before and after comparisons. But here's the one that jumps out to me. It's PI VI over TI equals PF VF over TF. And the reason I'm picking this is because they're giving us volume, they're giving us temperature, and they're giving us pressure, which we can use to compare before and after. So this is what I would go with. But it's asking what the new pressure is. And I would call this my final pressure. So I'm just going to refer to this as PF, my final pressure. So if we can, let's try to rearrange this equation. So what I would do first is multiply both sides by TF. So
By what?
for example, sorry, say that again.
You blurred out, so I didn't hear that
Oh, sorry.
last statement.
What I want to do is I want to try to isolate this on one side of the equation so we can solve for it. Make sense?
Mhm.
Okay. So let's try to do some basic algebra to get there. And in fact, I'm going to move this over to the side. Whoops. Just so I have enough space to really do this clearly. Oops. Okay. So we need to solve for PF. So first things first, I would multiply each side by TF. So PI times VI times TF over TI is now going to be equal to PF over VF. And then what I would do is I would divide both sides by VF. For PF. So now we've done some basic algebra to be able to solve for this. But this is good now because now we can plug in our numbers. And let's find our initial pressure. That's PI. In the question, it says that the initial pressure is 88.89 atmospheres. So I'm just going to go ahead and plug that in. So I'll say 88.89 atmospheres will be the first number. And then next, I need to find what VI is. That's my initial volume. And they say it's 1.432 liters. So I'll go ahead and plug that in. And then last but not least, we need our final temperature, which they tell us is 27 degrees Celsius. And we're going to divide this by, oh, sorry, I almost made a mistake. That should be temperature final, right? So the final temperature was 94 degrees. I almost made a big mistake there.
Can you, so I thought, can you do Celsius or do you have to transfer it to, doesn't matter. You can leave it in Celsius.
That's a good point. So as long as our units cancel appropriately, we should be okay. So let's double check that it cancels appropriately. So the temperature initial was 27.0 degrees C. So you see how we're able to cancel out degrees C here and here? In this case, I wouldn't bother with the conversion. That's just extra work. And then our volume final over here, we said was reduced to 0.932.
So I did a similar problem like this a while back with, it was on the homework, I think, and I went through it with the tutor, and we could not get the right answer when we kept it Celsius. We had to convert it to Kelvin and then convert it back. I'm not sure why it made a difference, but it did. But you're saying it just doesn't matter, right?
Actually, let me think about this. Sorry. I am wrong. You're right. We do need to convert it to Kelvin. I'm really sorry. I'm even making a mistake here. I'm having a brain fart, but let's convert it to Kelvin because it will give you a different answer. We need to make sure that we're using the proper unit. So let's go ahead and do 273. Let's add that in. Sorry about that. But thank you for stopping me. I'm glad I didn't just breeze through that. And the reason it doesn't work with just pure Celsius is this proportion is different when we add in the 273, right? So it becomes a different ratio of temperatures. So we do want to add that in.
Okay.
All right, so now let's plug this into our calculator and find what the pressure will be. So we've got 88.89 times 1.432 times 94 plus 273. It's my numerator. And let's see. I'm getting an answer of 167 point and then a bunch of decimals, but we should only have 3 sig figs in our final answer. So I would say that this should be 167 ATM. Be my final answer for that one. Thank you so much for catching that Kelvin thing. Sometimes I make mistakes too. So I'll just write 167 ATM right here so we can kind of keep track. Any other questions on this one? Oh. All right. So let's go to 14. What is the total pressure and torr of the gaseous mixture that contains 3 gases with partial pressures given below? The good thing is to find the total pressure, you just need to add these together. But what's one problem with adding them together right now?
They're not in the same unit?
Not in the same units, exactly. So what I would do is I would try to figure out a unit to pick. And in this case, they're not asking for a particular unit. So which one should we use? Anybody want to pick one?
Would torr be kind of the easiest?
Sure, let's just stick with torr. And luckily, 1 torr is equal to 1 millimeter of mercury. And then 760 torr is equal to 1 ATM. Okay, so let's convert this to torr. So I've got 0.845 ATM. I want to cancel out ATM, so I'm going to put this on bottom. I want torr, so I'll put that on top. We know that there's 760 torr for every 1 ATM. So that'd be 0.845 times 760 would be 642 torr. We've already got that one for the 135. And then we've got 195. We know it's going to be equivalent to 195 torr. So let's just add these all together now. So this was our first one. Our second one is 135. And then, like I said, 195 millimeters of mercury is going to be equivalent to 195 torr. So I've got 642 plus 135 plus 195. And I'm getting 972. Let me double check my work though. Yep. All right. Is that what everybody else is getting?
I got the same.
Okay, perfect. Yeah, one mistake students make is they just start adding things together without realizing the pressures are different. So sometimes just slow down and double check your work. All right, and number 15 is more related to chapter 4, so we can probably skip that one. But it's important to remember that a water molecule, we draw it out, its Lewis structure looks like this. It's not ionic, right? So I go ahead and say it's not an ionic bond. What holds together the atoms within the water molecule? It wouldn't be a hydrogen bond because that's what holds water molecules to one another, but it's not what holds the atoms together within a water molecule. And so then we'd have to say, well, is it a polar covalent bond or non-polar covalent bond? And I'd say, well, it's got to be polar because oxygen, it's pretty electronegative and it's pulling electrons away from the hydrogen. So I would just go ahead and quickly circle this as review. All right, let's go ahead and jump to number 16. So the professor that wrote this used to work in a military lab, which is why she has a lot of bomb examples here. She used to work on making top secret high explosives, which is kind of weird, but I promise it's not me writing about bombs all the time. So she's talking about a thermonuclear bomb, which is a hydrogen bomb that has a small amount of gas on the inside. It's actually special isotopes of hydrogen that they fuse together to form a heavier isotope. That's what releases an incredible amount of energy. And it releases a lot of power, but it's asking what's the new volume of the gas? So let's look at what we've got here. What I'm seeing is pressure, or sorry, volume and pressure before and after, right? So let's consider our original equation. So PI VI over TI equals pressure final times volume final over temperature final. In this case, we can assume that the temperatures are going to be the same because they aren't even telling us anything about temperature. So we could simplify this. We could say that pressure initial times pressure volume equals pressure final times volume final. And this is based on the assumption that the temperature is going to be the same before and after. So it's not going to play a role. All right, so what we need to do is we need to figure out our final volume of gas. So our final volume is going to be our pressure initial times our volume initial over our pressure final. So our initial pressure, if we look at it, is going to be 4.00 times 10 to the 6th atmospheres, incredibly high pressure on the inside of an atomic bomb. The volume was itty bitty, 0.0600 liters. And we're going to divide that by our final pressure, which is just the standard atmosphere of 1 atm. So let's go ahead and do this math. So I'm getting, what would that be? 2.40 times 10 to the 5th liters as my final answer. And that's what makes a good high explosive, is something that generates a large amount of gas really, really quickly. That's why these weapons are incredibly damaging, in addition to obviously the radiation and the heat. Any questions on that one? All right, the next one is kind of, I don't know if trick question is the right word for this one, but it's trying to test to see if you know which numbers to use and which numbers to ignore. So it says, given the following, and then it gives you a bunch of numbers. It says, calculate the amount of heat required to melt 30 grams of ice at 0 degrees Celsius. So they're not talking about increasing temperature. They're just talking about the energy required to melt. Okay? But let's start out with what we know. We know that we've got 30.0 grams of ice, right? Now the question is, which of these will we use? Will we use the heat of fusion of ice? Or will we use the specific heat of ice? Or will we use the specific heat of water? Which of these do you think is the most appropriate?
The heat of ice?
Yeah, I would immediately rule out this one because it's referring to water. So I wouldn't say it would be that one. But would we use the specific heat of ice or the heat of fusion?
Oh, specific heat regards to heat absorption, right?
Yep, so specific heat is looking at the temperature required, or sorry, the energy required to raise the temperature of an item. In this case, the question here isn't asking about increasing temperature, it's just asking about melting, right? So I would go with the heat of fusion. The heat of fusion is saying, what's the amount of energy required to melt something without raising the temperature? So in this case, it tells us that the heat of fusion is 80.0 calories per gram. So now we can cancel out grams. And what would that be? That'd be 2,400 calories. And this is what I was trying to drive home with the water lab, is I asked a question about why there were plateaus in your curve, right? And that plateau region is actually due to the heat of fusion, that it takes energy to break apart the ice even without increasing the temperature. So you don't see a big jump in temperature because all that energy is going to break up the hydrogen bond network within ice itself. It's kind of interesting to think about. Any other questions on this? Nope. All right, represent the following reaction using Lewis dot structures. Let's skip that one. That's just getting back to Lewis dot structure practice, which I think we've got down. And then the next one, when solid ammonium nitrate is dissolved in water, the solution becomes cold. The solution process is what? Exothermic, endothermic, neither, can't be classified, or both. Well, in this case, if it's becoming cold, does that mean it's generating cold?
No,
No. What's a better way of describing it?
it's absorbing heat.
It's absorbing heat, exactly. That's something that I really had a hard time wrapping my head around as a student, is that cold doesn't exist. Cold is the transfer of heat away from something, right? So your fridge, for example, it's not generating cold on the inside of your fridge. Rather, it's pulling the heat out of the items you put into the fridge and dumping that heat back into your room. So in this case, becomes cold is another way of saying absorbs heat. And any reaction that absorbs heat would be considered to be an endothermic reaction. And then the last one is, it's pretty good review. Which of these is most likely to be a covalent compound? And somebody asked in the discussion board, because they were getting confused on this again, how do we easily identify a covalent compound from an ionic compound? So what I told them was that an ionic compound is going to be one of two things. It's going to be a metal plus a non-metal, or it's going to be a metal plus a polyatomic ion. Or it's going to be NH3 plus a non-metal. That's another polyatomic ion, but ionic compounds tend to fall into these three main categories. All right, so let's see if we can find which one of these are ionic compounds. Well, rubidium is a metal. So I'd say that it's a metal plus sulfur, which is a non-metal. I cross that out and say it's ionic. Same thing with strontium, that's a metal, so that's got to be ionic. Magnesium's a metal, so that's ionic. Calcium's a metal, so that's ionic, which means that sulfur dioxide must be our covalent compound. It's between two non-metals. But that's good review. I think for the sake of time, we'll skip the extra credit problems just because we're almost at the hour mark. Is that okay with everybody? The answer is in the key. So if you want to just quiz yourself, some of these are a little bit more challenging, but they're excellent review to quiz yourself. But just to kind of wrap things up, I know a lot of people wanted me to go over questions 17 and 18 from the homework. So let's start with question 17. And it says that a solution is prepared by dissolving potassium chloride in water. And it says that KCl is a strong electrolyte. What does that mean? It means it dissociates and breaks apart into ions 100%, right? So what we could draw this out as is we could say, well, KCl, when we put it into water, breaks apart into the cation, potassium, and the anion chloride. Okay, when we look at this, we get 2 moles of ions.
Can I ask you a quick question?
Yeah,
How do we always, I can't remember how did you know that plus and a minus?
so the plus here.
Yeah.
Yeah, that's a good question. So potassium is in group 1A,
Oh, yes. Okay.
and that means it would be +1, and chlorine is in 7A, so it'd be 1 minus.
All right.
Yep.
Thank you.
So this 2 moles of ion is equal to our value N for these problems. So let's keep that in mind. And let's go to the equation that we would need from our notes. So in this case, it's going to be delta TF is going to be equal to N times KF times M. So N is going to be the number of moles of ions. KF was already given to us over here. What does M stand for, capital M? Does anybody know?
Molarity?
Molarity. So this is going to be moles per liter. So let's go ahead and solve for this because they're not giving us molarity. If you notice, they're giving us the mass and the volume though. So we'll just have to figure this out on our own. So we know that we've got 4.66 grams of KCl, but we need to figure out moles. So let's go to our book, and potassium is 39.10. And we've got chlorine, which is 35.45. So in this case, I know that there's going to be 74.55 grams for every 1 mole. And we can just plug this in. And I'm getting 0.062508,384. I'm just going to include all the digits for now. And then in addition, they tell us the volume is 250 milliliters. And we know that there's 10 to the -3 liters in every 1 milliliter. So this would be the same thing as just saying 0.250 liters. Is this making sense so far with everybody? So now let's figure out what the molarity would be. So I'm just going to take that top number that I got and divide it by 0.250. And I'm going to ensure that my answer only has 3 sig figs. So this would be 0.250 molar. So now it seems like I've got everything that I need to solve this problem, right? I've got the N, which is the number of moles of things in solution. In this case, we said there's 2 moles of ions. I've got KF, which is the constant that they gave us in the problem. And then we just solved for molarity. There's one last thing though that I wanted to hit on. Is it says, how will the freezing point of the solution be different? And then if you notice, it's got 2 options. Will it be higher or lower? What happens to a freezing point if we add something to it? Will it be higher or lower?
Lower?
Lower, exactly. If you think about putting salt on an icy sidewalk, it lowers the freezing point. So I would immediately go through and just cross out the ones that have higher. It couldn't possibly be either of those. But I'll avoid giving the answers away just to keep things fair. And then question 18 was one I actually put in the discussion board But I'd be happy to go over it now if you want. Or is everyone kind of tired?
I wouldn't
ahead.
mind seeing it.
Yeah.
Sorry. Do you want me to go over it?
Yeah,
Yes.
sure, go ahead.
Okay.
Yes, please.
Okay, so same idea. So osmotic pressure of the solution at 0 degrees C, and it says that AlCl3 is a strong electrolyte. Okay, so let's go ahead and think about this. If we put AlCl3 into solution, if it's a strong electrolyte, that means that it must break apart. So we're going to get aluminum, which in this case is going to be 3+. Oops. And we must end up with chlorine, which is always going to be 1-. However, we had 3 chlorine, so I must have the coefficient 3 here. What would the N value be for this one? How many moles are we getting out?
4.
4, exactly. We get 1 mole of aluminum and 3 moles of chloride. Okay. So for this one, osmotic pressure is the symbol pi, and it's going to be equal to N RT, or RMT, I guess. And let's go ahead and plug everything in. So N is going to be the moles. R is going to be our gas constant. M is molarity. Whoop. And T is the temp in Kelvin. Okay, so we just said that N is going to be equal to 4. Our gas constant, if you remember, is 0.0821 liters times ATM over mole Kelvin. Our molarity was given to us, which is 0.050 molar. And the temperature that's given to us is 0 degrees Celsius. Should I just plug in 0 here? No, we got to change it to Kelvin. So it'd be 273 Kelvin. And that will give us our pressure. But let's check one thing. We know that molarity is the same thing as moles over liters, right? So if I cancel my units, I'm going to cancel liters here, cancel moles here, and cancel Kelvin here. And my answer is going to be in ATM. So it's going to be some number in ATM. Okay, if you notice, 2 of the potential answers are in ATM. The other ones are in torr. So what I would do is I would first solve this and see if either this or this matches my answer. And then if it doesn't, what I may need to do is I may need to convert this to torr to check for those last 2. Does that make sense? Awesome. Any other last minute questions?
Would it be the same as using the other constant? Like if we wanted to just put the 24 liters of torr over liters, the other I think it's 64. I can't actually remember what the constant is. The other gas constant.
Yeah, that's a good question. I normally stick with this one right here. But I always double check that my units cancel at the end of doing my work. And if they don't cancel, then I know I'm running into problems. But personally, this is the number I remember going all the way back to when I was a student. And it's the one that stuck with me. I don't remember the one with torr.
Okay, cool.
Yeah.
No, it's just good that you can just do it with just this. It's just the same number. You just have to then transfer to torr. You don't have to memorize both.
Exactly. So you can always do the transfer at the end. Yep. Any other questions?
Can you give us any last minute like hints on what we should really focus on preparing for exam?
So I did try to trim it down to 15 questions because a few people said, I think it was quiz 6, they felt really crunched for time. So I would say try not to panic, especially on the math. You'll have enough time. But I will say historically, the area that students struggle the most with is, I give you the equations, but some students don't know which equation to pick or where to begin with setting up problems. So if you can, practice the end of chapter problems from both chapters 6 and 7. And just pick random problems and see if you can pull the right equation that you need and set up the question correctly. And the good thing is at the end of the chapter problems, I think it's the even ones, they have the answers in the back. So you can always check your work that way. But you can just take a scatter shot and see if you can answer those.
Thank you.
Yeah, no problem. The fact that you all showed up today means that you'll probably all do very well. The biggest issue I find are the students where they didn't watch the videos until like the night before the exam. And it just takes a while for that stuff to gel in your brain. And it requires practice and it requires review. It's not something you can just regurgitate on a moment's notice. So just keep on studying hard. And like I said, I felt weird having an exam due on Veterans Day because I know we have veterans in this class. But I also figured that everybody would maybe appreciate that extra day to have a little bit of time to let things percolate through their brain. So hopefully that works for everybody.
I have a non-related to this exam question.
Yeah.
At the end of our calendar, it shows cumulative, and for some reason, I thought we were having 3 split up exams we have had so far. Is that final exam going to be a cumulative final, or is it just?
It will be a cumulative final. I wouldn't let it freak you out though. So for example, a lot of students, they freak out and they think, oh my God, it's going to be an entire exam on gas laws, right? That's not what it's going to be. There will be questions about physical versus chemical change, right? Okay. Things like that, I'm hoping are just freebie points at this stage in the game. Yeah. Most students feel pretty comfortable as we go along with some of the easier concepts. So it's like, what charge does an electron have? And you're like, oh yeah, it's negative. If you would have asked yourself that in September, that might have been new and scary, but by December, you'll feel really confident with some of this material that we've worked through a number of times.
Okay.
Yep, so I wouldn't let it freak you out. I would say though, the study guides for every chapter are pretty helpful for going back. And it's never too early to start studying for the final. In fact, I was going to make an announcement for Thanksgiving break that students try to set aside maybe a day or two to just go back and review, because it's a good chunk of time that you'll have off. And it's time you could use to prepare a little bit for the final. That way you're not super anxious come finals week preparing for all your classes.
Do you know by any chance if you'll have sort of a practice final like you've had so far?
Yeah, I will. In fact, tomorrow my goal is to open the last modules, and you'll see that there will be a practice final on there as well.
Wonderful.
Yep. And we'll try to pace things so that we're not bunched up too much at the end. I may even trim a lab off. We'll kind of see how things go. But my biggest priority is getting everybody comfortable with the material.
Great.
Yep. Any other questions? Nope. All right, well, I might sign off here. It's going to take me a little while to process this video, and then I'll post it online. But if you have questions, you can email me or post in the discussion board, and I'll try to get back to you.
Thank you so much.
Thank you.
No problem. Have a good night.
Have a good night.
Good night.